Hi, everyone, and welcome. We are excited to have you all join us. Please feel free to use the chat to connect with fellow attendees and to share your thoughts during this session. If you do have any questions, please feel free to post them in the Q&A tab, and if time permits, we'll address them at the end of the session. Now, it is my absolute pleasure to welcome the presenter, John Mount. So let's give John a warm virtual welcome. Take it over, John.
Thank you very much, Patricia, and thank you all for attending. What I wanted to talk about in this session is time series forecasting. And it's a kind of a neglected topic in data science and something that I've dealt with a lot in my history in finance and other fields. So I'm going to just kind of skip introducing who I am, but we are in the R session, and I do have a book on using R, and which I'm quite proud of. So let me get control of the slides. So my motivation here is that I and many other data scientists feel that in data science, time series is kind of a neglected topic. And so here's Mark Elstersfun, staff scientist at Meta, saying that he really wished he'd had it earlier in his career, and I have to agree. And the reason that it's sort of late in many of our careers is it's slightly different than predictive modeling in a couple key ways, and it's very technical and sometimes needlessly hard to approach. So what I'm only going to do in this session is give you an outline of how to approach the field, though in the shared link on GitHub, which I've put both in the resources and in the chat and is also on the slides many times, I'm going to share a lot of software solutions, both in R and Python, to one example problem. And I'm going to give you the way to evaluate how the methodologies work without having to learn every scrap of the methodologies. So I'm going to motivate this, talk about time series forecasting, list out families of methodologies, work one example problem, which is the critically important problem of fitting sine x. So yes, it's a very artificial, silly mathematical problem. Then I'm going to bring in a sort of alien big hammer called Stan to solve it. And we'll see the nature of that solution. Stan's this kind of really neat Bayesian system that is very powerful. So what is time series forecasting? And I'm going to give somewhat of a heterodox view, which means slightly out of sync with the world. So do take it with a grain of salt. Time series forecasting, in my opinion, is the following problem. And this graph we're going to spend some time on. The x-axis of most time series graphs, and this one included, is time. In this case, and often in time series forecasting, we use time and date synonymously, and usually time is discrete, that days advance one at a time. And so usually time is discrete, and it's the x-axis, and the y-axis is some numeric quantity we're trying to predict. So on the left side of this graph, the dots are actual historical values over time. The lines are just there for legibility. And then the right section of the graph, the line is the prediction into the future. Notice there are no dots because the future hasn't happened yet. And the green are the uncertainty intervals of our model, which many of our modeling techniques can give uncertainty intervals. So the idea is, given only the past data, predict a plausible future, which is called a forecasting. And there's also a big issue to deal with that is often lied about, to be honest, in time series, is how far out are you predicting? Many people pass off a single tick, predict one time tick out model as if it's predicting many ticks into the future. In this talk, we are stopping our training data and our sensing data at time tick 980. And then we're predicting out many more ticks. So 10 ticks out, we're predicting 10 ticks into the future. And it's really important when evaluating models to discipline on that. Like, is your application needing to predict more than 1 day out? Often it is, that the easiest to predict is 1 day out, but that's often too soon to act on. So a more valuable prediction might be 10 days out because you may have time to take an action, even though that's obviously going to be a lot less reliable. So what is a good prediction? A good prediction is one that when the future events actually arrive, you see the dots are now populated on the right, they happen to be near what you predicted. So I just can't emphasize enough not to use the diagnostics of any modeling system, but to insist on out of sample evaluation of the model. So don't use the model supplied diagnostics, but just, force the model to make a prediction and then see if it's right. Now, of course, how do you know if a prediction is right in the future? It's like all things data science. You simulate. For instance, we had maybe data out to time tick 1000. We pretended the world stopped at time tick 980, and then we reserved that future data for holdout evaluation. I've often seen in time series, you rapidly get into bitemporal or having to deal with time notation. What did I think at this time? What time am I pretending now is? And you also have two notions of knowledge in time series. You have your training data, and you also have your sensing interval, which is you might be predicting Wednesday's number of restaurant attendees using Monday's data that you've seen Monday happen, and you're using a model that was trained over the last year. So business applications, I think, are very important in time series, though much time series literature is written for scientific applications. We're going to use only one pretend application, a restaurant that happens to have Sin X customers dining every day. So it's sort of a very artificial example, but the idea is to have an example where we know the right answer. You often see time series in predicting forecasting in businesses, future expenses, future revenue. You hear it all the time in the stock market, where you have very sophisticated things like stochastic calculus, which we're not going to get into. And some of the earliest stuff was tides. Like here is the 1876 Lord Kelvin's tide calculator. And it's a machine with these little dials, and you literally turn the crank to predict future tides. Really nice device. So we've done some demotivation. Sorry, we've done some motivation. Now let's do some demotivation. I agree with this announcement from the Facebook Profit team. Profit is a time series, a very good time series tool that Facebook open sourced in 2017. And they said basically it's kind of a great package on top of Stan because time series prediction or forecasting is sufficiently technical that you want to use a package to do it, that doing the Wild West ad hoc stuff can burn you. But the packages are so technical, you're unlikely to use them correctly. And so Profit binds in very well a lot of details of how to predict by day. So Profit is date-oriented financial stuff. So it's really good package. This is what I mean by my demotivating technical details. So a typical time series package, and this is an example from R, because I can see the arrow assignment, says that to do something like ARIMA, which is a acronym I'll define in a minute, you need to wade through pages and pages of diagnostics you've never seen before and check normality of residuals and independence of this and dependence of that and autocorrelated stuff, all kinds of things you've never seen. Just you certify whether the model will work instead of the software certifying it. Then, and this is again from their documentation, the model builds a prediction, and they fail to mention or notice this is a degenerate prediction. Just like in our original graph, everything on the left is historic data, and everything on the right in the blue uncertainty region is the prediction. And this model is saying it has absolutely no opinion as to whether the world's going to go up or down in the near future. And it says, not only do I not know what's going to happen, but I'm becoming less and less certain of even that because those error bars are opening up really wide, really fast. So you can fail much quicker than going through all the rigmarole the system point you through. And this sort of maybe the system is inherently unpredictable, or maybe the model failed. In this case, I think actually the model failed because ARIMA 311 is not the parameters I would have picked. The other demotivating fact is time series people hate variables. Now, what we call explanatory variables, which is usually the inputs to our machine learning or predictive models, they demote to calling external regressors. So when you're predicting the future, you usually use two things. You use recent behavior of the variable you're trying to predict. So if the variable we're trying to predict is number of visitors to a restaurant, we use recent visitors, the counts, recent visitors to the restaurant. And that's where the A in ARIMA comes from. It's autoregressive, AR. Auto means self. And then the external regressors are facts about the world you think you might know in the future. For instance, you can buy from Predict HQ what events are in your neighborhood. So as a restaurateur, you can know 3 weeks in advance, is there a movie on Saturday night? And obviously, many of those events are regular, but you can subscribe to them and get the magnitudes. Those are called external regressors, and you add them to your model saying, look, I know some things about the future that should affect your prediction. All of these, so when you add external regressors, you move in the ARIMA world. So ARIMA stands for Autoregressive Integrated Moving Average Technology. It's the most popular time series system. In fact, some people mistakenly think it's the only one, and it's certainly not my favorite all the time. Then you move from ARIMA to RMAX, X for external. The problem is no RMAX package actually tells you what it's, well, the RMAX packages don't actually tell you what they're doing, and often what they're doing isn't what you want. And Professor Hindman has a really good article on this, and it's basically you're forced to use what the package does instead of properly representing your problem, which is going to be the main topic of this talk. So let's go back to our families of methodologies survey. So in my mind, and this is where I'm a little heterodox, there's about 3 or 4 primary families of models. And anytime you count the number of ways to do things, you're going to be wrong. But in my mind, you have mostly the ARIMA-derived models, which I would include things like exponential moving average and double smoothing in there. You have the brute force methods, which used to be unpopular, but the neural net people have made them very popular for good reasons. And then you have the decompositional or hidden state inference methods. Those two method families are highly related, and that's where Profit and Stan come in. So packages. As part of preparation for this talk, I'm sharing all slides, rehearsal video, and worked solutions in R and in Python using about 7 different packages of the same problem. So you have complete code, including graphs of how to set up a time series problem and how to run it. I'm not going to share a lot of code in this talk. So back to our methodology survey. The ARIMA-derived methods all are of the A in ARIMA stands for auto, and AR is autoregressive. So I have not tried out SK time. SK products tend to be really good, so that's a great comment, and I apologize for that. So that yes, the SK time is probably excellent, so I should add that. Thank you. Anyway, so the ARIMA terminology is that you're trying to predict a value y at time t, and we use the subscript to denote time. And this model is saying that it modeled the world as y at time t is 1.975 of the previous y minus the y 2 time ticks ago. And this is essentially one way to write down sine x, that this is a recurrence relation that's true for sine x. And the process of modeling would be to find the 1.975 and the 1, or the negative 1, to fit those coefficients. And the regression with ARIMA residuals is the most popular and most well understood realization of RMAX. So whenever you're using an ARIMA package and it claims to do RMAX, just figure out, is it doing regression with residuals or not? Because RMAX is sort of a meaningless phrase, unfortunately. It got abused and misused and used differently in different fields. And the ARIMA people always insist on equation systems like the one here, where they have all these shift operators, and they're pretty unreadable when you first approach them. So the incompatible definition is from a Python package called PyFlux, which I actually did not work a demo with because it broke my NumPy install. And yes, I can solve install problems, but I didn't actually even like their formulation. What I want to look at is the equation on PyFlux. It says the delta to the d is the I, or integrating operator. And for many of our problems, d is 0, so the delta goes away. And it's saying that y at time t is some linear combination of previous y times plus some pretty linear combination of epsilons, which are external shocks or noises, but please don't call them noises, and a linear combination of external regressors, the x's. Now, what to look at is this is not ARIMA. This is not regression with ARIMA residuals, because the x's are contributing to y of time t directly, which means they would then contribute to the next time and the time after. And they don't have the shifted time indices like the shocks do. And so this is meaning that it models external regressors as durable. This is what an econometrician would want. It models an external regressor as something like change in seatbelt policy or a good review for your restaurant. And we'll get back to how to interpret these equations in a minute. So after the ARIMA system, you have the brute force systems. This used to be anathema or prohibited. People would make fun of you for doing this, but it's actually a really powerful system. And it's just the simple idea. If I want to know y hat at k time 10 time ticks from now, in ARIMA, you build only a model for y hat 1 time tick for now, then you iterate it 9 times more. So you plug in your prediction for tomorrow as if tomorrow happened, and then you predict the day after tomorrow. Then you plug that in and you recurse. Very dangerous. It can run away. The brute force method says, if I want a prediction 10 time ticks out, let's just build a predictive model where I show it the last few days as training data, and then I give it the future 10 ticks out as the thing to be predicted. And then you just build a catalog or album of these models. You have one model for 10 days out, another model for 11 days out. And when you need to predict 12 days out, you just pick that model out of the soup by the subscript and run the model. And you have some problems. It might be inconsistent. Your prediction 10 days out might be different than your prediction for 11 days out in a weird way. But this is a really good method. It avoids tons of problems and many neural net solutions to time series. This is their data preprocessing. So it's a really neat way to do things. Then we get to our last two families of models in our survey. And these are the decomposition or attribution methodologies. These are usually what your time series or forecasting customer wants. They say they want high quality predictions, but they actually want understanding. And these are the first methods that give you understanding or explainability. This is a picture of Profit from Facebook, and it automatically, for this data, generated this 4-panel system. The first panel is labeled trend, and it is basically a what does it think is happening over many years, because Profit is heavily adapted towards dates. So trend, like how your industry is growing, your restaurant's growing year to year. Then the next panel, which may or may not be legible to you, is weekly. It's the day of week seasonality. Are Mondays much less popular than Tuesdays at your restaurant? Then the third panel is the yearly seasonality, which means months. Is September much less popular than January overall years? And then the last panel is the effect of external regressors. Now, this is a very noisy, hairy panel because for our pretend restaurant, we have these events activating every day. Now, Profit is, again, whether there's an external regressor present or not is the variable we supply, and how many people it puts into your restaurant, if we're predicting number of diners, is what Profit fits. And Profit's idea is, if it can decompose the past into a sum or product, it can do either of these different panels, then, and each of these panels can themselves be extended into the future. Trend is stable, change to change slowly. Weeks and months reappear each year, so seasonality can be reapplied. And the external regressors, we claim that we're going to supply and we know them. Therefore, if the coefficients are the same, it can apply these. So it can extend all of these panels into the future. Therefore, their sum or product is the extension of a prediction into the future. And that's what you see on the cover of Bayesian Data Analysis 3rd edition also, is that these decompositions are what most clients really want. And we have a worked Profit example here. And Profit and Stan both sit on top of something called, I'm going to call it just hidden state inference, or Bayesian methods. And it's just the idea that if the parameters of your model affect the data, which is why you think they're model parameters, then knowing your data should affect what parameters you think are plausible. And what we're going to do is a generic Bayesian or Bayes' law inference. And unfortunately, once we have a lot of data and a lot of parameters, the Bayes' law inference is not that simple PA given B, PB given A that you can tattoo on your hand. It's that implies that, but to solve that, you end up having to solve certain numeric integrals to integrate out nuisance variables and other things. So you end up with this formula that is actually somewhat intractable. And what the brilliance of Stan, which again Prophet's built on top of, is you don't have to set up this formula. From your description of the problem, it infers what the formula should be by rules, because the Bayesian reasoning is very mechanical. And then it then solves the numeric integral. So sets up the integral, you don't have to see it, and then solves it, and therefore you get estimates of the parameters. So let's go to our example problem to make things much, much clearer. Our notional problem is we're modeling the number of diners in a restaurant every day. And we want to build a good model. So using the fact that restaurant businesses are somewhat stable, especially prior to COVID. And so basically knowing how many people dined last Monday is very informative. How many people dine this Monday? So we think the past is very informative. And we also think there's available external regressors, such as how large a movie is showing next week at the theater next to us, which is information we can buy from various data vendors. Now, I'm going to add the new ingredient to this. We're going to partition the restaurant's visitors or guests into two subpopulations, loyal and transient. This partition will let us explain how external regressors work and why none of the RMAX models ever describe it to us in a way that's useful. So the issue is, and this is the core issue in all statistical problems, the data is underlabeled. If every customer would just write on their forehead whether they're loyal or transient, then we would have much better data. Unfortunately, we only know the total number of customers, not how many are each sublabel. The formulas we're going to do is that the loyal customers are autoregressive. So the number of loyal guests, first line of the formula, the number of loyal guests on a given date is a linear function of two previous dates and a durable external regressor. Like, did we recently get a good review? Because we think that's going to contribute guests for quite a while. Or did we recently lower prices? Did recently a new bus stop get near us? So did something durable happen? The transient guests are just, you see, they don't have an autoregressive term in the transient guests. The transient guests are a function only of external regressors, unlike the loyal guests. There's no auto or feedback term in the transient guest line. So these people just show up, maybe they have a Groupon coupon, maybe there's a movie nearby. They show up for either unknown or known external to the restaurant reasons. Then the total guests is the sum of the loyal guests and the transient guests. The only things we observe are the total guests and the values of the external regressors. So we don't know if our restaurant is 90% loyal, 10% transient, or vice versa. So this is the grace of Bayesian modeling. You write down what would make the model easy, even if you don't know it. Need to speed up a little, I apologize. So can standard systems solve this? Yes. If B reviews force to 0, this is a regression with the REMA residuals. If B events is 0, it's the other variation. We put in our artificial data. We have our example holdout data. And this is the Stan result. This is everything. The top left panel of this is all the data. The dots are the data. The line is just there for legibility. The middle left panel is the models, Bayesian models inferred loyal guests. And they change smoothly. And that's our inference trick, is we're assuming they change smoothly and slowly. And it says that about 70 of your guests are loyal going up and down. The bottom panel, left panel, is the past guests assigned to be transient. It's saying it's about 10 to 15 of your guests are transient every night. So even this decomposition could be big money. Then each of these panels is projected into the future, and the sum is the predictions on the top. And this is the grace of using Stan, and that you can get a decomposition like this, and you get a prediction like this, and you get explainability. It turned out this was the highest quality model we predicted. We also got really good estimates of the external regressor coefficients, and that these are the actual values were 14.2 and 16.1, and we estimated about 13.6 and 16.0. So really good estimate of the regressor coefficients. One of them was a durable coefficient, tracking things like reviews that tend to durably bring customers or change the amount of loyal customers. And one was the transient coefficient, which is the events that do this show up and never come again. You don't want to confuse one for the other. Like you don't want to spend valuable marketing dollars on mere sales and vice versa. So even these coefficients are hard to get from the other models. This is just, we just set up the formula. This is the Stan code. I mean, yeah, there's some boilerplate on Stan, but it's basically, this is just a mechanical translation of the algebraic equations we specified in an earlier slide into vectorized arithmetic. This is, the first line is saying that the customers are a lag 3 system, and the next system is saying the observation is the hidden autoregressive customers plus the externalized customers. And then anything that we don't know, Stan guesses at. What we get back from Stan is a table of guesses. Each row of this table is one of 4,000 different guesses, and each column is an observation, like the number of customers at time 990 is Y990. And you get different incompatible guesses, which is why you get a distribution of predictions. Our entire thesis is, in business forecasting, ability to specify actionable structure beats forecasting technique. Your customers are not going to listen to the details of double exponential smoothing and unit roots in ARIMA models. They're going to want the attribution and decomposition of prediction to structure, and basically Profit and Stan really deliver that in spades. Thank you very much for your time, and we're sharing all the results here. And I may or may not have time for one or two questions. That was certainly a really good comment about SK time, and that probably is a very high quality package that I will try next.
Yes, thank you so much, John. For anyone in the audience, if you have any additional questions, please feel free to use the Q&A tab on your right-hand side. We do have a couple of minutes remaining.
What caused the almost binary nature of the transient guess? That was an artificial feature of the artificial example. Yeah, so it was basically, I put it in as a variable that was almost always 0, 1, just to make things easier. And your implied question is really good. No problem is as easy as this in real world. So this was designed to be very easy. Excellent observation. So LSTM is the neural nets that have time feedback, and very good technique. My last client had very little data, so we couldn't do things like that. But basically, they probably often do a data prep where they make it a predictive model, even though they're using LSTM. So especially if they need external regressors. So the data prep's still relevant, and the neural net techniques are super competitive, very good, but they tend to need a little more data. Cool. Well, I mean, out of respect for the next session and all, probably we should wrap up. And again, thank you very much for your polite time and attention. Everything, including a rehearsal recording, shared here, but I imagine PyData also shares the actual sessions. And I'm going to go ahead and, yeah, I don't know why I didn't try SK time, because the SK family is my favorite Python set of families. So I guess I don't know why I got distracted by stats models.
Yes, thank you so much, John. It was a great presentation. Just to reiterate, like you said, if anyone has any additional questions on our end, please feel free to use our Discord channel, which is available in the reception, or use the lounge feature for more small group discussions to continue that conversation. But yeah, like you said, we can go ahead and end this session today. Thank you all so much again for attending.
Thank you.